All right, so we left off talking about Rolle's theorem. I want to talk about example 5. So on this function, f of x equal to x times the square root of x plus 6, we're given the interval from -6 to 0. We want to show that the hypotheses of Rolle's theorem are satisfied. So we got 3 different things. So if we look at a graph of the function or kind of think about what's happening, we know that this is some sort of square root function being multiplied by x. If you want to see what that looks like graphically, it would look something like this. So we definitely know that the function is differentiable. There's no cusps or corners everywhere. And we also know that from -6 to 0, we don't have any breaks or holes or asymptotes or anything. So we do know that this function is definitely continuous and differentiable. Pen's dying here. Let me get another one. F of x is definitely continuous and differentiable on the interval. We also need to show that f of a is equal to f of b. So on this given interval, we usually call the first value a, and we usually call the second value b. So what we're looking to show is that f of -6 is equal to whatever f of 0 is. So let's do f of a, and we'll call that f of -6. So -6 times the square root of -6 plus 6 is going to give us -6 times the square root of 0, which would be 0. And we want to show that f of b, or f of 0, is the same. So 0 times the square root of 0 plus 6 is going to give me 0 times the square root of 6, which would be 0. So here we are able to show that f of a is equal to f of b, which in this case, f of -6 is equal to f of 0. Okay, so once we know that Rolle's theorem is satisfied and we can use it on this problem, we want to find the values of c that satisfy this conclusion. So we want to know basically on the interval from -6 to 0, where is that c, or that x value, where that horizontal tangent is. So first thing we want to do is figure out, well, where is that horizontal tangent happening? So we do want to take the derivative. So I'm just going to rewrite this as x times the quantity of x plus 6 raised to the 1/2 power. And I do want to apply a product rule here. So I called f my x, my f prime was 1. I called g this whole thing here. You did need to use the chain rule, but when you get to the inside piece, your derivative of your inside would just be 1 anyway. So your derivative would be 1/2 times x plus 6 raised to the -1/2. So when you put that together with the product rule, that's going to give you x plus 6 to the 1/2, and then plus 1/2 times x to the x plus 6, I'm sorry, times x plus 6 to the -1/2. So I'm just going to clean this up a little bit. I'm going to actually turn this back into square roots. This is really telling me that I have the square root of x plus 6, and I'm adding to that x over 2 root x plus 6. And I do want to just clean this up and add these together. So I do want to get a least common denominator. So it looks like my LCD here would be 2 times the square root of x plus 6. So I'm going to multiply my first fraction by that. So 2 times the square root of x plus 6 times the square root of x plus 6 in the numerator, and then 2 times the square root of x plus 6 in the denominator, plus x over 2 root x plus 6. So when you combine in your numerator of your first fraction, these roots actually undo each other. So you're really just left with 2 times x plus 6. And then I'm just going to carry over that plus x into the numerator now that I have an LCD. And then my denominator would be 2 times the square root of x plus 6. And then I can go ahead and distribute out. So 2x plus 12 plus x should give me 3x plus 12 up on the top, and then 2 times the square root of x plus 6 down the bottom. So that's my f prime of x finally. So that's what my derivative is equal to. So basically I want to know, well, where is the tangent line 0? Where is the slope of my tangent line 0? So I want to take this derivative and I want to set it equal to 0. So 0 is going to be equal to 3x plus 12 over 2 times the square root of x plus 6. You can put that over 1 and cross multiply, or multiply by the denominator on both sides. That's going to give us 0 is equal to 3x plus 12. And then I'm going to go ahead and solve that out for x. So it looks like -4. So this is telling me that at the x value of -4, which again is just representing that c, that tells me that the tangent line is horizontal. Or that's a notation where f prime of c is equal to 0. So that is the x value that satisfies our Rolle's theorem. All right. And I'll have you guys try this next one. So that's kind of similar to the first example that we went through together. So if you want to go ahead and try this on your own, I'll post the solution to this in my notes answer key. So you can show that your hypotheses of Rolle's theorem are satisfied. So again, the continuous differentiability and the f of a is equal to f of b. And then you can go ahead and find the values of c that are going to tell you exactly where this tangent line would be horizontal on this interval from 0 to 5. Okay, so I kind of had mentioned today during class that Rolle's theorem is a special case of the mean value theorem, sometimes abbreviated to MVT. And you'll see that its stipulations are similar to Rolle's theorem, but we're actually missing one. So basically the MVT says that there's going to be some f, or some function f, and we need it to be both continuous and differentiable on our open interval from a to b. So differentiable on the open interval from a to b, continuous on the closed interval from a to b. So in this case, we need a and b to be included in our interval. Here, it doesn't necessarily mean that a or b needs to be included. So basically what the MVT says is that if these things are met, so if we're continuous and if we're differentiable, there's going to be some number c, which again is just some x value, in this interval, such that f prime of c is equal to f of b minus f of a all over b minus a. Okay, well, what does that mean? Basically, this means that f prime of c is the slope of the tangent line. And it's telling us that there is some number x or some number c in this interval such that the slope of the tangent line is equal to, and this stuff over here, this f of b minus f of a all over b minus a, is actually equal to the slope of the secant line. So that means that some number in this interval has, or there is some number x in this interval where the slope of the tangent line is equal to the slope of the secant line. Well, what does that mean graphically? So let's say we have some x values a and b on our x-axis, and I'm going to put a point up here, and I'll call this y value f of a. I'll put a point down here, and I'll call this y value f of b. And maybe my function in between looks something like, I don't know, that. And let's call this point up here, let's call that C. So basically what the MVT says is that at this value C, we can draw a tangent line. And what it says is that there's going to be this tangent line having the same slope as the secant line through A and B. It's not entirely accurate, but hopefully you get the idea. So if f is continuous, if f is differentiable, here's my f of x function here, this kind of curved line that I drew in on this interval, then there's going to be some number c where the slope of the tangent line is equal to the slope of the secant line. So basically that's what that means graphically. So how can we represent that algebraically? So example 7 says, show that the hypotheses of the MVT are satisfied. So we're given this function x cubed plus x minus 1. Well, this is a cubic polynomial function. We know that cubic polynomial functions are continuous. There aren't any holes or breaks or asymptotes there. We also know that this doesn't contain any cusps or corners, so it's definitely going to be differentiable. So I'm going to say f of x is a polynomial. So it definitely is continuous and differentiable. And that is on the interval from -2 to 2. So then I want to find, well, what is that value of c, or that x value, that actually is where that secant line slope is the same thing as the secant line, or I'm sorry, the slope of the tangent line. So you can do this in any order. Usually I'll do the slope of the secant line first, but you can also calculate the slope of the tangent line if you want to. So again, we're given an interval, so I'm going to call this a -2, and I'm going to call the b 2. So when I set up my slope of my secant line, f of b minus f of a all over b minus a is really telling me that I want to do f of 2 minus f of -2 all over 2 minus -2. And when this says f of 2, that really just means evaluating this function up here at 2. So 2 cubed would be 8, plus 2 would be 10, minus 1 should give me a 9. And I'll do the same thing for f of -2. -2 cubed would be -8, minus 2 would be -10, minus 1 would give me -11. And then this denominator would be 2 plus 2, so this is going to give me 20 divided by 4. So the slope of my secant line would be 5. So then I also need to find the slope of the tangent line. And to find the slope of the tangent line, I need to take the derivative of this. If we're talking about tangent line slopes, we're talking about derivatives. So my f prime is going to be 3x squared plus 1. So basically, I want to know, well, where is this equal to this? So 3x squared plus 1 is equal to 5. I'm going to go ahead and solve this out for x. So 3x squared is equal to 4. That's going to give me x squared equal to 4 over 3, which is going to tell me that my x values here are going to be plus or minus the square root of 4 divided by the square root of 3, which is going to tell me that's really plus or minus 2 divided by root 3. And I also just need to make sure that this is actually in my interval. So if you go ahead and get a decimal approximation for this, you do want to make sure that it is in between -2 and +2. So if I divide 2 by the square root of 3, that gives me like 1.15. So 1.15 is definitely in this interval. And then if I do the negative of that, that would be -1.15, which is still in this interval. So this is telling me at the x values of plus or minus 2 divided by root 3. If you wanted to rationalize this, you could. I'm just going to leave it where it is. This is telling me that the slope of the secant line is equal to the slope of the tangent line. So at that particular x value in this interval from -2 to 2, the slope of the secant line is equal to the slope of the tangent line. Okay, let's look at just one more example. So we're given f of x equal to the square root of x minus 4 on the interval from 4 to 8. So if we're looking at what a graph of this might look like, we know it's some sort of square root function. We know it's shifted over to the right 4 units. So this is what the graph would kind of look like. It is definitely continuous on this interval. It is definitely differentiable on this interval. So our hypotheses of the MVT are definitely satisfied. So f of x is continuous and differentiable. On 4 to 8. And then I want to find the values that satisfy the conclusion of this theorem. So again, I'm looking for the slope of the secant line and I'm looking for the slope of the tangent line. So my secant, I'll call my 4 my A, my 8 my B. So f of B minus f of A, all over B minus A, is going to give me f of 8 minus f of 4, all divided by 8 minus 4. So if I do f of 8, that's giving me the square root of 8 minus 4, which is the square root of 4, which is 2, minus 4 minus 4, square root of that would just be 0, all over 4. So my slope of my secant line would be at 1/2. And then I'm looking for the tangent. So I'm going to rewrite my f of x before I take my derivative as the quantity of x minus 4 raised to the 1/2. And then I'll go ahead and use my power rule. So 1/2 times x minus 4 raised to the negative 1/2. And if I use my chain rule, the inside derivative would just be 1. So I'm going to write this as 1 over 2 times the square root of x minus 4. If you were to take that quantity, put it into your denominator, and then turn it back into a root, this is going to be what your tangent slope is. So again, I'm asking myself, where is this tangent slope equal to this secant slope? So 1 over 2 root x minus 4, where is that equal to 1/2? So 2 times 2, or sorry, 2 is equal to 2 times the square root of x minus 4. I just cross multiplied there. I'll undo the 2 by division. So it's going to give me 1 is equal to the square root of x minus 4. Square that, both sides. 1 is equal to x minus 4. So this is going to tell me x is equal to 5. So this is going to be telling me that at the x value of 5, again, the slope of the secant line is equal to the slope of the tangent line. So that would tell me that graphically what that would mean is if I were to take these kind of 2 points between 4 and 5, and I were to kind of, 4 and 8, not 4 and 5, 5, 6, 7, 8, 4 and 8, and I were to draw my secant line through those points at this x value of 5, if I were to draw my tangent line in, that's what's happening, is that this slope at the tangent line is equal to this slope at the secant line. All right, so it is your turn to try some homework examples. Let me know if you have any questions on anything.